You requested
0
them
because I'm
for
waking up at
graduation.
45 or 8.
It's a late game though, so you're fine. But like, he literally was like, "Well, you'll be one of the ones that like one of the first ones to walk." And I was
Alright,
like,
so
"Yeah."
here we go,
And he goes, "You just leave after that." I was like, "You can't leave
Gonna jump
graduation."
in.
That's how it works, man. That's how it works.
There it is.
Also leaving early for tennis. I might get there and leave right after
Hey, Dad,
this.
I have to stay.
Everybody will hear my
He's like, "Well, I'll go." I was like,
Last week,
"Thanks for that."
Alright, I'll go.
Alright.
Hopefully we'll have some time to work some problems today too. But I want to get you started on, I want to get you previewing the lab, get you started on the lab, and then we'll work some problems before we like break into labs. That's for you two at home. If anybody's watching this or some watches it later. I did post a video that kind of wraps up the rest of some work energy power information. So information wise, we're pretty much out there. We just have to add in a little bit of the calculus to make the physics C component. So that's what today is more than anything. But yesterday and the day before should have just been yesterday, and then some of should have been 2 days before, and then some of yesterday. But it got bogged down a little bit by wasted time. Like there was no pulling punches there. There was some goofing off. So I don't know how to just quit it. It's like I'm gonna say something harsh, but put an emoji on it.
And LOL at the end.
Yeah, LOL or LULZ or something. Anyway, I won't. So this was our lab. We had the launcher lab, and most of the data we were working on came from how it existed up here near the top. Because we talked about MGH of this first segment. We talked about how it went from MGH up here and converted all into 1/2 mv squared down here. So from potential into kinetic. So we treated our situation, we treat the situation as if potential at the beginning, kinetic at the beginning equals potential at the end and kinetic at the end of the ramp before it actually launched. Now, what was the point of actually launching? When it launched, it went a certain delta x or d, and that's using only a horizontal velocity. The VO it launched with is VOX, and delta x is VOX times time, and H2 is equal to 1/2 GT squared because VOY is 0 with a horizontal launch. This is all 2D motion stuff. So understanding these two principles, we could, because it launched, we could use the height to determine how long it was in the air, within reason, even in spite of any other like countervailing things like drag. It wasn't going to have enough impact to really affect the time much from what we could calculate. And then we could use this, where it landed, the delta D, the experimental delta D, to calculate an experimental VOX, which would give us an experimental VO of the launch, which would be the V at this kinetic energy. Hello? So that's why we launched it in the first place. The launch part was all so we could get to this V part, which would help us calculate KE and compare it to NGH. That's what happened in the lab. We treated this to be true because energy is conserved. However, what we said about this furthermore, and actually let's use a different color for this denote here, is that this is actually the sum of all mechanical energy. This is the conservation of mechanical energy. Turns out, in reality, mechanical energy is not always conserved. Energy in the universe is always conserved, but mechanical energy of, say, a system is not always conserved. So, the marble, as it flowed, down onto the ground, its energy, the energy it had as the system, did not conserve. We treated it as if it did. MGH and kinetic energy at the beginning equal MGH kinetic energy at the end. It was all potential at the beginning, so it had no kinetic. It was all kinetic at the bottom of the ramp, so no potential. That's why we plugged in 0 here. And then we just said that MGH change equals 1/2 MV change. The change in U translated to a change in kinetic energy. It's what we said. That's how you did it. That's all. That's what we were gleaning from the lab. Okay, this is just a debrief of the lab. However, there was some issues. You noticed that this was greater than this by almost twice as much, right? There was more stored energy than there was output felt by the rolling ball. Hello? We said, well, where did those come? What's the outputs? It turns out, in reality, mechanical energy is not conserved. Energy of the system is conserved so that inputs equal outputs. It's just the other output was this unnamed entity. It was work done by a non-conservative force. That is, non-conservative forces exterior to the system. That means forces acting on the ball but not by the ball. The ball rolling was due to the ball being on Earth subject to gravity. The ball being on the surface, the ball did not initiate friction. Its contact initiated friction. Are you there? So it initiated contact with the air, initiated contact with the surfaces. Those surfaces and air created contact resistive forces. Hello? They created a frictional force and a drag force. Each of those forces acted across a certain distance. A force acted across a distance. And as what we've been looking at in this unit is that when forces act on a distance, work is done. So work was done by friction and work was done by drag. All that work was opposite the motion, so it was negative work. Hello? In other words, why did this number appear to be somewhere like 36 to 40 joules, and then our KE number end up being something like 18, no, it's more like 19 to 23. 19 to 23 joules. How is there such a discrepancy? A lot of it went here. We'll say that's the Y variable. There's a Y amount of joules that was done by the non-conservative work. The way we make this, the way we'd say this though, is that like the MGH or UO minus the non-conservative work equals the KE.
What is U again?
Hold on one second. This is indicating why non-conservative work is considered negative work. It takes away from the input, translating to actual motion. Are you there? Ideally, we think all of the input is stored, becomes moving. Stored energy becomes moving energy. Hello? That's ideally what we say. But not all the stored goes to moving, some of the stored. Because the stored makes a deposit in the non-conservative work bank. So some of the stored brought down, and then the remaining stored turns into motion. Are you there? That's how we treat it like a negative. This is sort of an aside. When you treat it like a negative, though, you can see that because of equal signs, we can just put it on the right side. In other words, there's energy produced or given to the non-conservative work. What does, what mean again?
U.
U means stored energy. Or potential energy. What?
KEO is just kinetic energy?
KE is kinetic energy. KE is kinetic energy. O means beginning. KE without it is just kinetic energy sometime later. UO, potential energy at the beginning. U is the potential energy sometime later. In other words, what we're saying is it went from all stored to all kinetic. Ethan, what you got?
So theoretically, if you had a long enough ramp and you let the ball had enough, could roll for a long enough time, most of this potential energy could be converted to partially kinetic, but it could turn into heat. So what if you had it long enough where it can melt the ball?
Theoretically, that would be possible, but you'd have to have a sealed container inside. You have to have an insulated, sealed container to trap all the heat. Otherwise, the heat would leave the system because heat emanates. Heat emanates to where there's lower heat or lower energy, so it would flow away from the ball. The ball would be generating friction, or it would be like an area hot spot, and everywhere not there would be less hot. So energy would flow from the hot to the less hot, unless you insulate it, like did it in like a cooler, right? Like a Yeti cooler. in which case, at some point, you have a really long ramp in a really ginormous Yeti cooler. You could melt the ball.
By using the work of gravity.
Yeah. Eek. And if you made the gas really dense, it wouldn't flow as fast. You get a really steep ramp and really anyway. There's some other things that kind of brings about. The bottom line is this non-conservative work, just as an aside, not physics for this class type of thing. It could be it's the next physics really. We have thermodynamics is the physics 2 course. Is this non-conservative work transmits into heat and disorder. So this is how energy is conserved with friction. Because you're like, well, where's friction in there? Well, I mean, where's the heat generated? Doesn't it give off heat also? Well, no. It gives off energy as work, non-conservative work. The non-conservative work translates into heat energy. Hello? So just so we're like tying a bow on this, it's not stored energy, motion energy, and non-conservative work and heat. No. It's saying the work is non-conservative and then there's heat also. Hello? Theoretically, if you paint this picture even further into the thermodynamics chain, you can say the heat plus the work at the beginning is equal to heat plus the work at the end, and that the work done is kind of broken into the potential and kinetic and the non-conservative work. At some point, if given enough time, all of this W shrinks until nothing, and the heat should get bigger until maximum. The heat, everything's kind of going towards heat, and then heat dissipates into disorder, and so actually we're cooling off as a universe. But that's just sort of trivial type stuff. Again, here up, this is home. All right, we're going to land the plane. I want to give everyone what they need here. All right, so if mechanical energy is conserved, this is what it would look like. Friction and air resistance are considered negligible if mechanical energy is conserved. But it turns out they're not in real life.
Will there be like a question that said if mechanical energy is conserved, then...
Sort of. It'll say if mechanical energy was conserved as the marble went down, how should the amount of potential energy at the top of the ramp compare to the amount of kinetic energy at the bottom of the ramp?
They should equal.
Okay.
And then it says, you'll notice they don't, because it says find the difference between calculated potential and kinetic. How were these two values? How close were these two values? And then, was mechanical energy conserved?
Okay, I got you.
You see? Yeah. So that's why that addresses that going on there. Furthermore, work non-conservative, just to break this down, is still a force times a distance. The question is what force? You've got frictional force, kinetic energy, kinetic friction. But also this, as that ball rolls, this indicates that the ball is sliding at some points. Meaning there's not a great grip between that slippery ball and the metal ramp. Hello? But also, the ball rolls a little bit too, right? Which means there's some Fs acting along the distance that the ball moves as well. Hello? Hold on. If the Fs is causing it to roll, then the ball is undergoing two types of motion. Down the ramp and rolling as it goes. So really, we can break this up even further. There's energy in the roll as well. When we're doing 1/2 mv squared, we're assuming it's moving down the ramp like a block moves, sliding across the surface. But it's not. It's sliding and it's rolling. This introduces us to another concept of kinetic energy. We've got kinetic energy of translational kinetic energy and kinetic energy of rolling. So 1/2 mv squared is a translational motion, and then the remaining bit is rolling kinetic energy. I'll let you digest that in a minute. I put that up yesterday, but not everyone got to see it. What is that?
UT.
It's a gravitational potential energy. U, potential energy. G means gravitational.
Well, I thought so, but like, what is that?
That's MGH.
Oh,
So what you would notice is the question says, if mechanical energy is conserved, then
what'd you get?
UG equals KE. You'll quickly realize that UG does not equal KE.
I put KE on.
The first reason we identified it doesn't equal KE
So
is because of the non-conservative work. But that's not the only reason.
that's close
The
to
other
what we did
reason
not actually do.
UG is not equal KE is because we didn't account for the rolling motion that was
Especially
attained by the ball. That's not UG.
It's
So, like what we're saying is stored energy was transmitted into some movement down the ramp. That's called translational energy. Some of the energy was transmitted to the ball in its rolling. That's called rolling kinetic energy. And then some of the energy was lost to friction and air resistance. That's work NC, work non-conservative. The formula for kinetic energy of rolling is I times omega squared. I is a concept known as inertia. We're actually going to address that more deeply in the rotational unit. But just for the purpose of this lab, we're going to just dive into it feet first, or head first. So I is sort of like mass. Let's just look at these equilibrating here. If kinetic energy of rolling is 1/2 and kinetic energy translational is 1/2, that makes sense. Kinetic energy translational is 1/2 of the mass. That would be 1/2 of the resistance to move. That's its inertia. Mass means its resistance to move. I is the resistance of an object not to move, but to roll. So that's why I is similar to M, but based on rolling motion, not sliding motion. Are you there? They're similars. Okay? V is the speed of an object's straight line motion. Omega is the speed of an object's rolling motion. So everything has its equivalent from translational to rolling. Because the ball does both, we have an energy of translational and an energy of rolling. Both of those are subsumed in the same thing. And just in case if you're not following it because you weren't here, we're saying this. MGH is essentially equal to 1/2 MV squared plus 1/2 I omega squared plus work done by the non-conservative force. And it was something like, my data ends up being something like, in terms of the millijoules situation, mine ends up being like 10, nope. Oh, well, if I used the colliding apparatus and I used my ramp apparatus from years past, when I used the ramp with the bigger ball, I had 41.34 millijoules, and then my KE was 20. I did two different trials, so one was 22 and one was 26. I'm going to use the better trial, 26.39 millijoules, and then I got 10.56 using this formula. The way you use this formula is I had to tell you some features about the marble you used. I had to tell you you already had the mass of your marble, but I had to tell you the radius of your marble. And then you could use the velocity that you found, divide by the radius to find the omega, square it, and you end up getting, you can plug into the equation. This turns out that 1/2 I omega is 2/5 mr squared times v squared over r squared. Sorry, this should be r squared as well. The r squared's canceled, so radius didn't even matter. It ends up just being 0.2 m. Did I say 2/5? Yes, 2/5. 1/5 or 0.2 m v squared is this rolling amount of kinetic energy, KE rolling. Hello? Now, if that's still, once again, that's too technical for what we're doing right now. The takeaway for this unit, now we're going to dive into that, and it's going to be applicable for future units. So seeing that shouldn't shock you, but the weeds of it may be like, okay, what, like the I and the M, where you get these numbers from. Where I got those numbers from are not important. You need to know essentially that this is not perfect. So these are the added components. There are other components involved. Okay. Now, if we just let a brick or a cube slide down the ramp and launch, we wouldn't worry about this at all. We'd only have this. Now, get this before I answer your question. This non-conservative work is based on friction. Friction is required for the ball to roll. Hello? So there's no way it could roll without generating friction. Therefore, we had an exaggerated amount of work done. Theoretically, you slide a cube down the ramp, you won't have this as large a percentage of work done by non-conservative forces. Or at least potentially. That would be a hypothesis I would make. I haven't tested that. That's not out of a textbook. I'm totally speculating on that one, but I'm fairly certain it makes plenty of sense because you need friction to make it roll. But go ahead, what you got?
I was actually going to follow up with that. I was going to ask it a bit earlier, but if you did have that cube and it was in the same scenario, would the overall velocity be greater than the ball or not? Or like more friction might be involved?
That's a good question. It'd have the same MGH. So theoretically, yes.
It was the same mass.
Same mass. And anyway, check this out. If you were to say ideally MGH equals 1/2 mv squared, they did this for you in the analysis part. The v is equal to square root of 2gh. You do some algebra to get that. Mass is nowhere to be found. Mass doesn't matter. Even the type of piece of object doesn't matter. Now, that's saying mechanical energy is conserved. Is it conserved? No. And if it's not conserved, then what else matters that we're saying doesn't matter? How about what it's made of? If it's a rough, bumpy sort of brick, well, that's going to make work non-conservative a little bit bigger. If it's a smooth brick, shiny and smooth, then maybe that's going to decrease the non-conservative work a little bit more. And maybe it's less than this non-conservative work. Okay? What you got?
So the 1/2 mv squared is the sliding force, the sliding energy, and the I omega squared is the rolling. So
Correct.
you're saying it's rolling and slipping the whole time?
Oh, it is slipping. But even still, even if it doesn't slip at all, if it just simply rolls. When an object is undergoing rolling motion, you take two things are happening. The center of its mass, and I use a black dot to represent this. Notice the black dot is traversing in translational delta x. But if you were to put a dot on the surface of the rolling object, the red dot represents this. The red dot is representing a motional change of theta. And as theta changes over time, that's called omega. As the translational distance from black dot to black dot to black dot, that's delta x. It's a different type of motion. This one is a translational linear vector motion. This one is a rolling circular motion. Are you there? So they're distinct.
So what if we knew that it was only rolling? Would you even include the 1/2 mv squared?
That's what I'm trying to say is even when an object rolls, the center of its mass moves translationally.
Okay.
See, that's the center of the dot represents how it translates. The red dot represents how it rolls. Both are happening, so both are true. Always, no matter what.
So then you put both of them in the equation.
What indicates the slipping part
The WC.
is the WNC FK. What indicates zero slippage at all? FS. If it only rolls and no slipping, then this is all the non-conservative work. If it slips a little bit, that's some of the non-conservative work. That's some of the non-conservative work. course, drag is also involved always because it's always in air. But yes.
Are there any scenarios where those two would like counteract each other? Like it would slip, but then it would roll backwards, like the opposite direction.
No. Yeah, I'm trying to imagine it though. I'm saying no, but I'm still hesitant. I can't say definitively. Okay, yeah, so that's my answer I'm sticking with right now. I'm still gonna say I'm at like 80% on the software update. Okay. All right, continuing along. My data, actually I just listed up on the board, I should have put it up here, is saying that MGH equals 1/2 mv squared plus 1/2 I omega squared plus work non-conservative. I got 41.34 millijoules on the ramp with the larger ball, and then I calculated 26.39 millijoules of the kinetic energy if mechanical energy was conserved. And then I calculated using this equation, same thing as what I instructed on yesterday, and I got 10.56 millijoules, it's not milliliters, millijoules. And then the non-conservative work I just found was the missing component, the missing piece each time. And so I got 4.39 millijoules. It's the work done by the non-conservative force. Now, it'd be harder to measure this, but if we knew like the circumference of the actual ramp itself, we could theoretically use that as an entire distance. This would be equal to the frictions K and S. If we could say, all right, guarantee this sucker is not slipping, has no slippage at all, has a good grip. We could say Fs times the distance of the ramp. We could find the static frictional force that was used to cause it to roll. Hello?
Mm-hmm.
In which case, mu K times Fn. Or excuse me, not mu K. I got that look. Mu S times Fn. And then we could find that mu S. Are you there?
Using W and C. Okay.
There are multiple, look at how many things we could find out. It's not mechanically conserved. We can find non-conservative work. We find rolling friction or rolling energy involved. From rolling energy, we'll look into rotational motion. We could find other variables, and we'll look at those when we get to that point. But yeah, pretty cool stuff here. You okay? Okay, cool. And this is all more or less still explained in some detail with the concepts of the video. Okay? You have all seen that work is the dot product of force times the displacement over which an object is pushed.
Can
Right.
you explain dot product? I tried to follow during the video, but I was kind of confused
I mean,
about
what does
what
it-
exactly it's for.
What does it mean?
Dot product means that only the parallel force matters for the energy involved. Now, you may feel like, well, hold on, an object, I've got it somewhere in here. Hold on. Here we go. Look. So, dot product. We're saying that only the component of a force dragging an object that that is parallel to the distance it traverses, only that does work for that distance. So yes, this force is you expending energy to apply it, to pull at something at an angle. This textbook is a good example. If I take this textbook and I pull it open like this and I drag it across the table, I'm applying a force at an angle. Okay? When I drag it at an angle like this, it moves a distance x, but the distance x is parallel to the table. Right? The work done to make that move happen was solely due to the horizontal component of my diagonal force.
Okay.
So when you like read it in the equation, what do you do?
You say we're only concerned with the horizontal, so any force applied, we're only concerned with the parallel, so we call F cosine theta. The way this translates into just a generalized work formula is we say, all right, F dot D means F times D times cosine of the angle between them. If you multiply the force vector amount times the distance vector amount times the cosine of the angle between them, you'll be good. If the angle is 0 between them, meaning straight line force, okay, then cosine of 0 is 0. I'm sorry, cosine of 0 is 1. So F times D times 1. If the angle's greater than 1 or greater than 0, then it's going to be F times D times a fraction. Hello? So to generate the maximum amount of work, you want to apply force that parallels the distance you're pushing something. That way you can say all of the energy I'm putting into this is going into this object moving that way. Hello? Otherwise, I will expend a certain amount of energy, but I'm only accomplishing some work. The accomplished work is what we're talking about, parallels. Are you there?
So the dot product is just so that you can relate F to F cosine theta.
You can relate input force to the output work.
Okay. I think I'm following.
The force I'm applying, the only thing that translates to output work is the horizontal component of my input force. That's why we use the cosine theta.
So would we use a dot product in our own sense? We would just put the overall force rather than the specifics.
Right, the overall force, yeah.
So if you use the specifics, we just do normal multiplication.
When you do specifics, like you would have already found the horizontal component.
Yeah.
Yeah. If you pre-found the horizontal component, yeah, you multiply, because that presumes the D, the F, and the cosine theta already. Yeah. Now, dot products are also what's called scalar quantities. They produce just a magnitude. This should make sense in one regard. You know, when you take integration, you take the antiderivative of something. You have to do you do the function of the antiderivative, but you always put plus c because it's a constant. This is related to the fact that you can't be certain there wasn't a variable that was eliminated when it was derived, or there wasn't a constant that was eliminated. You can't be certain about a constant that may have been present prior to. This is related to that. That's just a side note for those people who are in calculus. It's not necessary. We'll also put it on the board. But into the calculus a little bit. Since work is force dot x, what if we had a force that was not constant? Okay. How can we determine the work of that? We would integrate that function, the function of a non-constant force. But hold on, before we understand the non-constant force and integrating a constant that non-constant force, let's look at it as if it was a constant force. If we were to plot the graph of a force applied as you push to a certain x distance, you could get a line of force versus x right here. Finding the area means integrating. This area equals the work. So we're saying work equals the integration of from x0 to x is the f dx or fx dx. The calculus part is that the integration of force times x just means let's calculate the work done of each segment over distance. Check this out. If we were to take this earlier example of the work, earlier picture here, if we were to apply this force and we found the work done of this segment, and then 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 this segment, and 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 then add them all up, that is the process of integrating. Just taking snapshots and adding up the small micro-sized snapshots. if you can make the snapshots be milliseconds long and all back to back to back, as the limit approaches infinity, the number of things or the segment size approaches 0. Are you there? And you added up each segment of work done, that is what integration does. So just again, demystifying that, but applying it to the physics part, to the physics that we've already done. It's really just, you need to understand this in a conceptual sense. We're not going to do any integration in this class. If they did, it'll be a very rare kind. It'll be a very simplistic kind. They'll give you a function for force. They'll say integrate it. You take the antiderivative of it and you plug in numbers. That's it. By the way, we'll know if that's going to be a possibility by seeing it on my AP. Either now in the unit or when I give you some practice questions in the future. I've yet to see it. So there's your evidence first. It would be a total shock if they included you having to do the antiderivative in any functional sense. But let's just walk through this here. If we had a function for f, let's say some force was applied non-constant. Let's look at that in a different sense. One way we could have force in a non-constant sense is at a consistently increasing sense. Find the area of it, and there you go. Another instance would be if you had a force versus x, where like you push for a little bit of force, but you get tired, and you push for another force. And you find it in your strength to push some more, but then you're really tired, and you push some more. Are you there? If you found the area of, there could be a function to represent this force. Find the area of every segment. The area still equals the work you did. Hello? This would be a non-constant force.
Is work the derivative of force then?
Work is the integral of force Fx.
Okay.
Yep. Now, we remember force is a function of ma, though, right? You know, force is equal to ma. So, ma, sorry, this is ma x dx, because the delta x doesn't go away. And you know, a is the derivative really of just velocity. So a is dv dt, right?
Yeah.
Go plug it in. M a dv dt x dx. What happens when you take the derivative of, or the antiderivative of a derivative?
That's the original answer.
You just get the original, which would be v. So when you take the antiderivative of something, of dv dt, and you raise its exponent up to v, and then divide by the exponent, 1/2 mv squared, does that look familiar? That's the kinetic energy. Hello? So if you stepwise follow this down, this makes sense. Okay, work translates into motional energy. It's fair? And then if you translate this the other way, is that if you translate this a different way and you say, all right, force acting on an object on a ramp is supplied an mg, a weight force. Yes? And over the distance that it's high up, the distance is an h. mgh, well, that's ug, gravitational potential energy. How about that? Or GPE, as it's also called, but UG is a little bit more common. Hello? All right, so then we're saying that work are these other things. They're equivalent in this capacity, in this whole integration capacity. If we take the integration of, if we integrate the energy, the stored energy, alongside the work here, okay, and we plug in along down the way, we get the kinetic energy again. But also, there's one more piece to point out here. We take the energy over here. Yeah, actually, I forgot. I need to scrap this part. I don't know why this is even here. Sorry. But that does lead us to kinetic energy as well. That's just another view of it. If we do say that instead of work, we say potential energy, the change of potential energy, stored energy goes from all stored and not moving, and then I let go, and it goes to no stored, all moving, right? That's the change of potential. Change of potential is based on the integration of fx dx. It's the same thing as before. But let's look at it in the flip-flop. To integrate this side is to say we derived the other side. So that force is equal to the derivative of u dx. Hello?
Yes.
Watch this here. Let me see this one more time. So fx equals du dx. Do what? What did you say? What did you say?
I said it's still some of this.
Okay. So, but let's break this down here. Let's rearrange this like equationally. F times dx equals du. F times a small delta x. D is just a small delta, a small change. All we're saying is force delta x is equal to a change in u. Change in work. I guess work does change u. I just preached. Work changes u.
Amen.
Do you see the double entendre? It changes the letter U, which represents potential energy, but it also changes you as a person. Ha! Work changes you. And it usually stores more of you in there. You know what I mean? It makes you better.
Wait,
Okay.
delta U equals delta E, so equals delta V. What?
That's delta U. All right. Anyway, notice here just the algebra here. If I just rearrange this, and then if I were to take the integration, f dx equals du, I integrated both sides. This would leave f x dx equals u, which is to say this. This is just a reversal. These are reverses of each other. Hello? Alright, last concept and we're done with the unit. Oh no, I forgot about this. I forgot to point out this piece. What if the force is a constant change, like a slope like this? What this is saying is that as force is applied more, it goes a further distance. Or let's reverse it. As a greater distance is applied, the force increases as well. When could we see something like this occur? How about an elastic band? Stretch it a little bit, some force is applied. Stretch it some more force is applied. Stretch it some more force is applied. Hello?
This is the spring thing.
Yeah, this is the spring thing. This says that as force goes up, or as the stretch goes up, a force required to do it must go up too. So we said this when we said the spring force. The spring force is equal to K times X. As X goes up, the force goes up by a specific factor called K. If we plot that, this is what it would look like. Hey, wait. We said when force is plotted against X, the area is the work done. If force is plotted against X, the slope is the K. This K is called an ideal spring constant. Are springs ideal? Most of them are not. Are rubber bands ideal? No, because they're not springs at all. But we can pretend and treat them like an ideal spring, and our physics will be sound enough that we can make some predictable approximations that will be reliable as time goes on for short periods of time. In other words, if we were to determine what the K value for this rubber band is, it would be true and worthy for a couple weeks until we wore out the rubber band. Hello? Things wear out. That's why there's not ideal. Also, not everything's exactly like a spring. They're close enough, and that's why spring gets this S symbol to illustrate its elastic. The S subscript of a capital F refers to elastic. Hello? So one more step further. If we take the area, so the slope is K, that's the ideal spring constant. If we take the area of this force versus X equation, we said the area is equal to energy, U or W, some sort of change to energy. Okay, area then of a triangle in particular is 1/2 base times height. So 1/2 X times F, 1/2 F times X if we rearrange it. The height of that triangle is F, the base of that triangle is the X part. That's how you find the area of that shape. Are you there? Okay. Well, what did we say F is equal to of an elastic object? F is equal to Kx, right? So if the area is 1/2 the F value times X, and F equals Kx, can we not substitute it in? Yes, we can. Yeah, we can. So 1/2 Kx times X. Oh, wait. 1/2 Kx squared. Paint that picture a little bit more carefully here. K is the constant. Force is Kx. Fs is Kx. 1/2 Kxx. 1/2 Kx squared. That means there's a change in energy that's equal to this 1/2 Kxx, which means if we stretch something a certain distance, based on the K, there would be stored energy. What does that mean in this instance? What does it mean for there to be stored energy in this rubber band?
Wherever you let go of it, it's gonna snap.
It would hurt somebody. So energy, it may improve you, but it also hurts people. No, just kidding. No, it leads to injury. It can lead to injury, but also injury makes you better. Those are synonymous. To get injured is to also improve. That's a weird. That's a weird meandering to get there. But we're pain and suffering while improving leads to improvement. Anyway, what you got? While you work.
So if I'm training and then I break my leg, that's improving?
No, if you're working hard and if there's pain along the way, you're gonna improve still.
But then, like, even though he improves from, like, his legs being broken, he's never gonna be back where he was.
Not necessarily.
But what if I
Depends on what kind of break it was. Most breaks you actually are stronger than.
I mean, say you're a football player, you're probably not gonna be able to.
No, and you're that's too far, too far. The bottom line is this: is that there's no way to work hard without the potential for or the existence of pain and suffering in some regard. And work hard is translational to goodness and improvement, and hard work. So that way, hard work plus pain equals improvement. This is why nobody cares work harder. You know, in a reductive sense. Yeah. Here's the big thing to take away is another equation. US is 1/2 Kx squared. It's on your equation sheet. Should you find it?
Oh, you want us to look at it?
Yeah, find it too, so we can identify it.
Should you be on? Oh, I found it.
That was good.
Wait, it says delta X.
Yeah, that's the one I was using. That's close to.
Yeah.
I found a cake on
Yeah, so what's the delta
So
X?
from nothing to something. Because it's also non-legal x. It just has 1/2 Kx squared. In the old equation sheet, like 2 years ago, it was just an x. The delta x is a new phenomenon.
Good.
Did you find, what about F equals Kx?
It has
Yep, and that's because when I pull on this rubber band, the force of the rubber band is opposite my pull. The negative indicates it's a counterbalance, right? It's a resistive force. The elastic force is a resistive
So
force.
do you actually value it, or should we use it?
You need to use the negative as a concept. So that way, if you said, how much force do you need to apply? Positive number. How much force does the spring apply, or does the rubber band apply? You should think it's opposite, so that's what the negative's taken care of when I think of it as an opposite. The value of its oppositeness is going to be equal. If I pull with 10, the rubber band's pulling with 10. Oppositely.
So you just
By
need-
saying opposite, I don't have to put negative 10.
Okay, so you just need to know that it's negative, but you don't have to use
Right, you can use it both ways. You can use it both ways. You can get away without using the negative by just saying like this. I pull with 10, the rubber band pulls oppositely with 10. Or I can say I pull with 10, the rubber band pulls with negative 10. 6 in one hand, half of the other. Or 10 in one hand, negative 10 in the other. Okay. All right. You got those equations there. There's one more equation here in this unit, and that is power. P is for power. Power. P is for power. Power is the amount of work done over time.
If you expanded that equation, you can end up with this huge thing just equal power.
What?
Like if you
Yes.
broke up time
Yeah.
and if you broke up
Yeah, I will.
W.
So, and this is fun too, is power, its units are capital W, and of course it means the ever favorite watt. Power is in watts. My second or first favorite unit. Hertz and ouch and watts are my favorite. Watt? This is the unit for power. It's in watts.
Okay. Question. What is this equation? Is
Watt is this.
that the equation?
Okay, so this is the simplistic form. If you were to say the change in work over change in time, obviously no work ever happens without time changing, so that's sort of presumed when you say work over time. Work is equivalent to a change in energy. So I could also, just to really make this, in years past, they used to just say that, which is it's like this 1/3 of the possibilities, but reduced down into a simplest version. It meant you had to think with some conceptual ideas. When you see work over time, you have to think, all right, well, things change when time changes. There's no time happened, just happens, it changes. So then work must change anyway. The delta symbol is subsumed inside it. It doesn't have to be explained. Also, now I guess when they remade this equation sheet, they said, we're only going to use one of these because of space. So they chose this one this time. I don't know why. And even more so, they did replace the delta because this is physics C. A small change is as the limit of the length of time approaches 0. D, dt. D is the same thing, and that's why they
Well, I
changed
knew
it.
that,
Okay.
but I just didn't know why.
Is it delta V over delta T with the acceleration?
Just wait. So let me answer Ethan's situation because this is where we're going anyway. Turns out, remember, work is force times distance, right?
Mm-hmm.
So force times distance over time. Distance over time is velocity. So work is also force times velocity.
I mean, power is work times velocity.
Power is work times velocity. Yeah.
It shows
No,
up as a-
power is force times
Force
velocity.
times velocity. Okay.
It shows up as a dot product because they can be like multiple different angles.
That's like an angle.
This subsumes, so force times V or force dot V.
But that's only at one
The distinction between using a dot means multiply and a dot as meaning dot product is that the dot is normally a little bit thicker, but not necessarily. It's almost the difference in thickness of like you put a dot as like an elevated period on the page, and then you put bold. You put that text in bold.
But it'll be obvious that it's dot product on like a question.
Well, it's more like on your equation sheet, they would say work is F dot X delta X, and they put the little arrow hats on top. And so this means dot product, and you're supposed to know F times X times the cosine of the angle between them. They put this, they assume you to know this.
Okay.
I saw that.
I can judge.
They also assume now that you're in the since this is the physics C course, they say XO to X, F, they don't have to do dot in this case because this already presumes that, F delta X dx equals work. They also want you to know that that's the case.
Great.
But we're not going to do anything with that. We just need to know that if we see this appear, it shouldn't shock you. This is mostly going to be a conceptual exercise. That's why we leave it as where we leave it. But wait, there's more. What if you take this a different direction and you say, okay, force times distance over time, and then, well, force is also ma, so that'll make you mad over a period of time. Or if you really want to have a nickname here, Mav. Maverick. Mavs.
Because all of us are Maverick.
I can't remember the power equals Maverick.
Power equals Mav. Anyway. Is that where you were going? Do you have any more?
No, I was asking if that F times velocity equals power, if that would only count for power in a certain specific moment in time.
No. It's as F applies to an object, giving it velocity, you can determine the power involved. How much work was used over the period of time for that velocity to occur?
But for their force to be there, that means their acceleration. And then that means that velocity is changing. Which means the power is changing. Right?
Power you spent. You have a fixed period of time. Like it's a period of time that has an end point. It's not collectively all over the place.
So I was asking if that would, the power is spent, so as the velocity gets greater, that's the more power you spend. Okay, yeah.
Okay, but generally the approach is to call this an average velocity. So we don't have to worry about changes along the way. Hello? Okay. So FV, F times V there. And one more thing just to put things into reality here. You know, your parents may call it the lot bill.
A what?
A lot bill.
Oh,
You gotta pay your lot bill. I gotta pay my lot bill. What they mean is power bill, right? You know, power as a power bill is actually given to us as a kilowatt. Kilowatt hour. It's reported to you as a kilowatt hour. And the units for watts, right? Watts is work over as joules per second. So they're literally saying kilojoules per second times hours, which let's extrapolate that out again. Kilojoules per second times 3,600 seconds. What they're really saying is not, they shouldn't be calling it power, it should be called energy. They're actually telling you that your energy consumption. It's reported with specific units called kilowatt hours. Why? Because the numbers are like less than 3 digits usually. They can be like, hey, you used 8.6 kilowatt hours. Okay, instead of giving you like 8,643,000 joules. That gets a little clunky. So they can reduce text and it saves everybody money and time and space.
That'd probably be pretty scary too.
Yeah, you'd be like, what? How many millions of joules did I use? Okay, cool. It's only like 11.6 kilowatt hours. So, oh, okay, well, that's not so bad then. Hello? Just welcome to reality. That was all to say about that. There is one more thing to go with, and it is understanding that you can have elastic energy. This is our elastic energy. These are really all of our equations going on here. What if we had some stored energy in an object, and it translated into motion, and then translated into gravitational potential energy, some stored energy. What if we had something that was elastic? If we treated some elastic object like an ideal spring, what if we treated it like an ideal spring? We could store energy in it in a stretched distance, flexed distance, right? And then that would be stored elastic energy in its stretchiness. It would cause it to move. And then as it moved, it would reach a certain height where it was all stored energy. Hello? If it's all stored energy, then we could determine some factors about it if we knew how high it went. Like how much energy was stored in it elastically. If we know how much energy is stored in it elastically, then we can find out what the constant of stretchiness it is. The K constant.
Oh no.
And so we will. The challenge is to find the K of the popper.
Can I take a shot in the dark and say 0.8?
Nope. You have to show and prove why. So, in your lab notebooks, you're going to do conservation of energy lab, conservation of energy concepts of elastic energy for this popper lab. Storing energy in the popper, determining
I need to skip one.
the
right?
K value thing. So they're here, procedure in your lab notebook, write a detailed procedure, step by step, not like forever long, just step by step. How you plan to determine the elastic potential energy stored in your popper launcher system. We're using the popper. Include all measurements you plan to take, list the equation you plan to use, make a data table to organize your measurements. This is sort of your basic foundational page. We'll run the lab. You're gonna need at least 4 trials, since there's probably a lot of error involved in the lab. Based on your results, how much elastic potential energy was stored in the popper? How much energy did the popper have after being released? I crossed off popper because we used the marble, but this was, we actually couldn't find when I made this originally, we couldn't find the launchers until this point, so this is our first time playing with the launchers for some of these students. So, and I also didn't have poppers at that point in time.
Is this number 12?
This is lab number 12.
We don't have to write the other 11 in the lab notebook, do we?
No, but before you start on this lab notebook, I've got a new lab notebook for you.
Yay.
I mean, nothing
And you have to use these because we bought them with a certain kind of grant money. So if you'd like, you can tear out all your pages, the good and the bad, the pages of the carbon copy and the real ones. If you haven't already turned in your carbon copies. By the way, that's all we're doing today.